My name is Adam. I'm a software engineer in the Graph Data Science team at Neo4j. And today I'll be talking about how to run graph neural networks at massive scale using some tools like graph sampling and the GDS Python Client. So let's have a look at the overview for today. So we'll talk about just introduce the problem we're trying to solve, which will be the data set that we're going to look at, and then the problem itself, which is called node classification. And then we'll look at how to approach this problem using graph neural networks. And part of this will be doing just like a very brief overview of what GNNs are to get some intuition there. We'll talk also about PyTorch and the PyTorch geometric, which we'll use to actually implement graph neural networks later. Then we'll talk about some pros and cons of GNNs, why they're good and some limitations, and how graph sampling can be a way of getting around some of the limitations. So talk about graph sampling, one particular graph sampling algorithm, which is random walk and restarts. We'll talk about the Neo4j Graph Data Science library, which I work with, that will allow us to do this. Then we'll do the demo, and we'll try to sum up towards the end and talk about what could be our next steps. I'll also say that I'll not be taking questions during the talk due to the time limitations that I have. Instead, if there's time at the end, I can do some questions. Otherwise, I'll respond to them asynchronously in the chat afterwards. Okay, so let's get started. So what are we trying to do here? So let's talk about the data set that we're going to look at. What we'll use today is the Cora data set. It is a research paper citation network. So we'll have paper nodes and sites relationships. You can see the plot in 2 dimensions to the right here. So yeah, there are about 2,700 nodes and 5,400 relationships. And additionally, each paper node will have a length 1433 binary feature vector, and this vector will be representing like a bag of words, basically. So each dimension will say like it will be 1 in the value of the vector if a certain keyword is in that paper and 0 otherwise. And additionally, each paper node will also have a subject. And in the plot to the right, you can see the color coding also by subject. You can see they sort of there are actually 7 subjects here. Yeah. Okay, and then let's have a look at the problem that we're trying to solve on this data set. So talk about node classifications. Node classification is a problem of having some nodes and a label for the nodes, or some of the nodes, but not all of them. So in this case, we have our example, or like a small subsample of our example to the left here. We have some nodes that are labeled red and green here, and they are belonging to two different scientific subjects. And the gray nodes are the ones that we want to predict what subject they belong to. And that is the node classification problem. And you see here the cogwheels in the middle is us actually solving this problem. And the input is the graph itself, the nodes, the relationships, and also the feature vectors, as you see here. Okay, so this is the problem we're trying to solve. So one way to approach this would be to do like basic regular machine learning. So we just take our the vectors that we have for each node, this bag of words vectors. We train some neural network model, and eventually we can predict the paper subject. And this is totally like feasible. That's one way to solve the problem, but we're not really using any relationship information. Okay, so how could we do that? So one way could be to add the node degree, so the amount of neighbors in the graph that the paper has. So how many other papers does a paper cite? Okay, that could be one way of integrating some of the relationship information into our problem here. But I think we can actually do better, and that is where graph neural networks come in. And that is a way of doing, as we'll see, graph topology aware deep machine learning using relationships. Okay, so now let's just do a very brief introduction to GNNs. So GNNs, it's a neural network architecture, as the name implies, based on message passing, and messages are sent on the relationships in the graph. So the inputs are the same as before. We have the node feature vectors that is the input to the GNN, and the architecture is defined such that layer connectivity in our neural network is defined by relationships. So that is how the relationships come into the picture. So let's look at an example here. So here we have a small graph. This is not the graph we're going to look at later. This is just a small example graph. So we see here to the left, we have a target node A. And then for A, we can define the computation graph. And that is really the computation that GNN will do in order to predict a label for A, for the target node A in this case. Okay, so what do we have? So if you can see, in this case, we have 3 layers: layer 2, layer 1, and layer 0. And the layer 0 is like the node feature vector, the bag of word inputs that we have. And they feed into the next layer, depending on how the graph looks. So, for example, in the last layer 2, sorry, where A is the output, we can see that the inputs to that layer is B, C, and D. And those are, in fact, the nodes that A is connected to in the original graph, in the input graph. And that is how the GNN is defined. And so the same goes for B at the top here. So the inputs to B are C and A, and that's what B is connected to in the input graph as well. And then on these layers here, there will be some computation. We'll talk about that momentarily. What's to note here also is that this is actually just a computation graph for A, the node A, but there will be a similar one for every node in the graph, but they will reuse node vectors and weights. All right, so that's a GNN on a high level. So now let's look at what actually goes on in these layers to do these computations. So the GNN layer. You can say that it abstractly consists of 2 parts. The first part is aggregating the neighbor input. As we saw, we can see here to the right, we have some neighbors coming in with some information into the layer. So one part is aggregating that. The other part is updating the node, the B node here, the output from the layer with some sort of neural network, some sort of neural computation. And in fact, the aggregation can also be neural. Okay, so we'll see here. So the update is that, so for example, the B to the very right here is not the same B that is on the top that goes out. That's like the first one is the input to the neural network, and the second one is after some transformation, the output of the first layer. So they're going to be a little bit different. Okay, so now let's look at an example of a very famous GNN architecture and how the layer is defined then. Okay, so here's a very complicated equation, so you don't have to mind so much about the general definition here. But we can see to the right here that what we do is that we aggregate, we sum basically together the node feature vectors of the nodes A and C from layer I minus 1. So we're going to compute something for layer I in this case. So we're summing together the features here. And there's some normalizing factor here that is based on the node degrees of the particular nodes involved. It's not so important. The basic thing is that we sum together everything here, basically, the node features from the previous layer. And then we do some neural transformation with some weight matrix, WI here. And then on top of that, we put some nonlinear activation function like ReLU or sigmoid or something like that. So this is GCN, and this is a very simple, elegant architecture, but turns out to be very effective. All right. So a way to implement GNN is to use PyTorch. Okay, so what is PyTorch? It is an optimized tensor library for doing deep learning using GPUs and CPUs. And in fact, it also supports distributed system and multi-GPUs and things like that. It was developed by Meta and now part of the Linux Foundation. It has a very rich ecosystem, and there's a lot of tooling for doing serialization and deploying models and things like that. So it's a very nice library. Though it's written mainly in C++, the low-level operations, and the C++ libraries that you need for GPU and so on. It has interfaces for both C++ and Python, and we're going to use Python today. And then there's PyTorch Geometric, which is an extension to PyTorch for doing graph learning, which we're interested in, of course. And notably, it has support for lots of GNN architecture, in particular the GCN architecture that we just looked at now. Okay, and now let's talk about some pros and cons of GNNs. So why are we talking about GNNs? Well, as we can see, they leverage the topology, the relationships of the graph via this message passing mechanism. The layers, how they're connected in the node network is defined by the relationships in the input graph. So that's very cool. That's something that is already better than what we had initially when we just used some neural network on the original node input features, right? Okay, and we also see that there were some weights on each layer, so it can capture a lot of information here. It's a deep model, right? It can capture a lot of information. It has great capacity for learning, and that's good. Okay, and another very nice features about GNN is that they are inductive. And essentially what this means is that you can train GNN on one graph, and then you can apply it on another graph if that graph that you're applying on is similar to the one you trained on. In particular, it should have the same like node input features. So if you, in our example, we would have to have the same sort of keyword representation for paper nodes in the both graphs, both the one we trained on and the one we predict on. And typically also want the topology to be somewhat similar. All right. Okay, and then what are some downsides of GNNs? Well, they require a lot of memory. So you saw that you can have many layers, and there can be many weights in each layer. So that's a lot of memory. And for similar reasons, they're very slow to compute. It takes a lot of time. There are computation graph for each node, and lots of weights and so on. So it takes a long time. And even if you have a GPU, it can be quite time-consuming. So this is not so good, especially since we're talking today about doing machine learning at really big scale, right? So this is the two big problems we have. If you have a large graph with lots of features, node features, then this will be a problem. Okay, and additionally, they are also hard to interpret because it's a deep machine learning model, deep neural network. We don't know how to interpret them very well. That's just the case. And they can also get fairly complicated to implement. Today we looked at GCN. It's one of the simplest ones, but there are also, there are other ones that are definitely more complicated. Okay, but so now if we zoom in on two of these things or three of these things, we can use the inductive idea here that if we can train train the model, the GNN on a smaller graph, we can maybe use it to predict on a larger graph. So in particular, if we take a sample of the original graph, train it on that, it will be faster because it's a sample, it's smaller. And then because the GNN is inductive, the model is inductive, we can then apply that trained model into the entire graph. Okay, so that can be very useful. It will save a lot of time, and the model will still have learned enough, hopefully from the sample, that it can sort of generalize to the entire graph. Okay, so now let's talk about graph sampling. How would we do this? So one approach is to use random walk of restarts. That's one sampling algorithm. And it's the following. So it's actually very simple. So what we do is like we start somewhere in the graph, we choose a root node, and then we just take random walks from this root node. By random walk, I mean we take some steps, and every time we do a step in the graph, we go to just a random neighbor. Okay. And then we restart from the node intermittently. And when we walked for long enough and we have visited a large enough part of the graph, that will be our sample. That will be our subsample of the original graph that is output of the sampling. Okay, and it was shown by some researchers that this produces a structurally representative subgraph, which is what we're interested in here, because we want the thing we train on, the sample, to have a similar structure so that it generalizes to the full graph later when we do prediction. Okay, now let's look at what we can use to actually do this sampling, to do random walking restart. So there is the library I work for, the Graph Data Science library at Neo4j. So what is it? So it's a plugin to the database for doing analytics. It is part of the server process, as you can see here to the right. So the Neo4j is part of a JVM, and GDS, the plugin, is also part of that JVM. Okay, and then you communicate to it via Bolt or Arrow, as we'll soon see. And how it works, it projects the data that you have in Neo4j database into memory. So typically you will have a lot of your database might live on disk, but then when you want to do analytics with GDS on it, you will project it into main memory and do analysis there for performance reasons and so on. Okay, and this library it provides high performance graph algorithms, which is great. So you can run on very, very large graphs. And in particular for us, which is very useful, is that it has a good implementation of random walk restart sampling, which you want to use, right? So we can take a very large graph and we can run sampling on this. That's exactly what we want. Additionally, we can do transfer to and from this JVM, the Neo4j process, because GDS has support for something called Apache Arrow memory transfer. So Apache Arrow is a memory format that allows for very fast transfer of data, basically, using the various Arrow libraries that goes along with that memory format. And that is something that GDS implements. So we can have this Arrow client transfer memory in and out of GDS very quickly. Okay, but this is a little bit complicated. So it's actually a better way of doing this, because what we would have would be like, would have some application here that uses the Neo4j driver, communicate via Bolt, would have some Arrow clients in that application as well, and then we also want to have our graph neural network as well. So, but we can actually do it a little bit simpler, and this is what we can do use to do that. So Neo4j Data Science library has a client. It's a Pythonic surface for GDS, which wraps the Python driver. It looks very similar to GDS Cypher API, if you have seen that. And it has some additional very nice convenience functionality that data scientists may be used to. And in particular, it uses Arrow under the hood to do very fast data transfer whenever that is possible for particular GDS endpoints. So we could use this to transfer data very quickly to and from GDS, which will be useful for us. Since we're gonna, in our case, we're gonna use a small graph, but in reality, you might have a lot of data, right? It's very easy to install. You just pip install Graph Data Science, and that's it. Okay, so that's the Neo4j Graph Data Science client. Now let's have a look at a demo using a Jupyter notebook. So I'm going to switch here to a different tab. I believe this is the tab. Okay, so this is a example notebook that lives in the repository of the Neo4j Graph Data Science Python client, so you can access it there. You may have seen it already, so I'm going to go through it today with you. So first, we'll need to import a bunch of stuff here. So you'll see we have pandas, we have the Graph Data Science object, and we have a bunch of PyTorch things. And and then we'll set some random seeds here just to make sure that we get the deterministic results. It doesn't really matter that much because I run this notebook several times with different seeds, and it's the difference isn't huge, but just something we're going to do. Okay, so let's do that, and then let's initiate our Graph Data Science object. You'll see that here. So we can. So basically, what we do is we create an object that through which we can communicate with GDS, which will be part of this Neo4j database process. So we just give it our credentials and the connection information, like the URI and so on, and then we're good to go. We also specify that we want to use the database called Neo4j of the Neo4j database management system. Okay, so this is the default database actually. Okay, and then we can use a function called load Quora. So you can call this directly here on the GDS object. What we'll do is it will use Arrow that we looked at just now to transfer data very quickly to GDS and project the Quora graph that we looked at initially. So now we have that in GDS, just using this convenient method here, load Quora. Okay, I'm going to zoom. I got some requests to zoom a little bit. So, okay, I hope you can see better now. All right. Okay, so we have the Cora loaded into GDS. So let's make sure that it's actually what we expect. Okay, so we can print the graph object that we have got back here. And we see, yeah, Cora is the name. And the node count looks right. And the relationship count looks right as well, according to what we looked at previously in the presentation. We can also see that there's a paper node label, which is good. Okay, it looks correct. And now we can actually, since we have the graph projected into GDS, we can use the algorithms of GDS to do stuff with it, right? So we're going to do sampling now. We call the procedure this way. So it's an alpha procedure. It just got released in GDS 2.2, which was quite recently. So what we do here is that we get a new graph by the name of Cora sample, which is based on the original graph G, Cora. And we set some random seed and concurrency to 1 just to get a deterministic sample here. All right, and let's see what we got. Okay, so we have 406 nodes and 532 relationships. And I should also mention that actually when you do by default, the number of nodes you will sample from original graph will be 0.15 here. So I didn't add that as an argument, but that's the case. And so that's why we get 406 nodes, and that's what we want. Okay, so we have this sample that is a lot smaller. It's just 15% the size of the original graph, which is great. Now we could train on this, right? And it will be a lot faster than the original graph. Okay, so let's move on. So now we need to get the data out of GDS, out of the JVM process of Neo4j and so on, to get it to our client side in order to be able to run the GNN with PyTorch and so on it. So what we're going to do then as a first step is we're going to stream the relationships. And you see that also went very quickly. So it's the procedure right here, that relationship stream. It takes basically just takes all relationships and streams them back, and using arrow under the hood, which makes it very quick. So let's see what we got then. Yes, so we have this pandas data frame. It has 532 rows, which looks correct because that's how many relationships we saw that we have. We see that we have some node IDs and target IDs that represent the relationship, and it also says what type it is. You can see here that the relationship, the node IDs are quite high, the numbers are quite large, and that's something we'll have to handle later because PyTorch geometric, it expects the node IDs to be from 0 and then consecutive. So that's something we will have to handle shortly. But otherwise, it looks correct here. So let's go to the next part here. And that's actually like massaging this data frame a little bit because currently it's not in the format that PyTorch wants. PyTorch wants this that you see here below, which is a list of 2 lists. The first list contains the source node IDs, and the second contains the target node IDs. And there's a convenience function on this data frame called by_rel type that does this transformation for us. So I'm just going to call that. And then we can inspect exactly what we got. So what we got back is a dictionary, which has all the different relationship types. We only have one. We only have the size relationship. And we can see that the length of the list of So it's a dictionary with the key sites, and the element or the value for the key sites is a list of length 2, and the first element of that list, which will be this here, the source nodes, is of length 532, which is what we expect as well. So it looks correct. Okay, so if you don't catch all the details here, you can just go back and look at the notebook later, and you'll see that I'm not lying. All right. Okay, I'm just going to look at the clock. Okay, so additionally, we have the relationship information now on client side. That's great, but we also need the node input feature, right? This bag of words. So we're going to stream those back as well using a different procedure called node property stream here. We're giving it our sample, and we ask for the subject and features node properties. This will be the bag of words feature vectors, and the subject is what we're trying to classify, right, with our GNN. Okay, so what did we get back? It looks correct. So we have 406 nodes, We have some node IDs. They are the feature vectors, and the subjects, that's what we want to classify in the end. So that looks great. Okay, I'm going to move on here. And this cell here does this transformation that I referred to earlier, that we have now. We need to sort of normalize this relationship list to be so that the node IDs here are basically 0 and 1 and so on. They can't be these large numbers. So this cell here is just going to do that transformation. I'm not going to explain how it works because we don't really have time and it's not really that interesting. But if you want, you can have a look at it later. So I'm just going to call that. Okay, and now we're going to create the input data to the PyTorch model we're going to train. And to do that, we need to create the edge index, which is just giving it this list here, list of lists, the map source node and map target node. So the same format we had before, but now they are remapped using this function here that we just called. So we're going to give it that. That will be the edge index. That will be the redshift information that PyTorch geometric needs. Additionally, we're going to create two vectors here, or two matrices rather, or PyTorch tensors, if you will. So we're going to give it from the sample node properties that we just got. We're going to give it the features. That's going to be one matrix. That's been the X, the input matrix. And for the Y, the output matrix, with the sort of the subjects or labels in our training, we're going to give it the subject column. The subjects of the papers here. Okay, so we're going to do that. And we see we have some data object here. It has X, it has some length of the node feature vectors, the number of nodes, etc. Okay, so before we train, we're going to do also now a split of the data, because when you do machine learning, you typically want to make sure that your model is correct. In order to do that, we're going to have a test set. Okay, so we're going to have a train set and a test set. We could have a validation set if we want to do some hyperparameter tuning, but in this small example, we're not going to do that. To make the split, there's a transform. The notion of transform is in PyTorch, and PyTorch geometric has this random node split transformer that we're going to use. Okay, so what does it do? So we create a transformer. We say that we want a test set that has 40 nodes and a validation set that has 0 nodes, and the rest will be in the train set. And then given this transformer, we can transform our data. So let's see what happens if we do that. So first we print the transform data, and we see now that additionally to what we had before, we have different masks. We have train, validation, and test mask, and those will tell us, or rather, those will tell PyTorch what nodes are in the training set or what nodes are in the test set, and so on. We can also see that the number of the training examples was 336, which looks correct. It's just 406 minus 40, which we put in the test set. Okay, that's great. So we have our data. Now we want to train a model on it, right? Okay, so that's what we're going to do here. So this part is really from the PyTorch geometric documentation. So basically just copy-pasted it and modified it slightly. So all credit goes to them. Let's just go to it quickly. So I'm going to run this. This is the definition of the GCN. It inherits from a PyTorch module, like all models in PyTorch, basically. And then we have this GCN conv. This is the layer that we import from PyTorch geometric that lets us define these GCN layers that we saw before in the slides. So we have the input size is the number of features we have on each node. Then we're going to have an intermediate output size of 16 for the first layer. And then the second layer takes that input and then outputs number of classes, which in our case will be 7, I just happen to know. So we initialize that. What's going on here is that when we call init, it will initialize the weights and so on that you need for these layers. And then we also define the forward step, which you have to do in PyTorch. It's nothing special for PyTorch geometric. And we get the data object here that we defined above, or that we will input that we defined above. And here we define sort of the forward computation, the forward computation of the neural network. So we take the data, we split it up into the X, which will be the input from the nodes, and then the edge index, which will be our relationships, as we saw before. And we just defined the computation here. So we use the convolutional layer. Then we have a ReLU after that. We add a dropout here to have some regularization. And then additionally, we use the last convolutional layer here. And we output a logged softmax. So, and reason for doing log softmax is instead of just softmax is for numerical stability and performance, basically. Okay, so this is our GCN. And then, okay, so we defined it now, and that seems to work fine. And the next step here is to set up, basically initialize this. So first, we're going to see what device I can use. So this is just we can check, okay, do I have a CUDA GPU on my machine? Then use that, otherwise use a CPU. And we can see here that I indeed do have that. So this will run on my CPU. And what we do here is then we initialize the GCN, and then we send the memory of the GCN, the weights, to the device over PCI Express or whatever is on my machine. And then we also send the data of the input to the GPU as well. And lastly, here we also define the optimizer that we're going to use. We're going to use the data optimizer with some learning rate and weight decay. That we may tweak with some hyperparameter tuning or something if we had time for that. We also can print the model here, and we see that it looks, I think, what we expect it to look like. Again, you can see here that output labels are indeed 7. Then we're going to do training. I'm just going to run this now. It will be fairly quick. And okay, and then, so we did some training. I don't have time to explain it, unfortunately. I can see. But let's also run evaluation. So here, this is a very standard PyTorch training loop. So if you want to look more into that, just look at the PyTorch documentation. And the evaluation here is also very standard. So this is basically how you could use GDS with sampling and PyTorch for the full workflow. What's missing here really is actually like running the model that we train on the full data set, the full Cora graph, not only the sample. That we will leave as an exercise. And then eventually there will also be we'll have some cleanup here. So we'll drop the graphs from the GDS Neo4j process so that they don't take up memory. Okay, I will head back to the presentation now. Okay, so that was the demo. Now just try to summarize a little bit what we learned. So you can see that node classification was an interesting problem here. We used it on this small scientific example, but it's also applicable to real industry examples like fraud detection and so on. We also saw that it could be useful to leverage topology when learning on graphs, not only using the node features. GNNs can do this well, we also noticed. But since GNNs are inductive, we can train them on a subsample. PyG can be used for GNN training. We can subsample using something like run-of-worker restarts. And we can use GDS, including its Python client, to do this run-of-worker restart sampling. And GDS supports rapid transfer capabilities, and that will enable us to do this very quickly, even though we would have large amounts of data. I would also just give a shout out to my wonderful colleagues Mats and Florentin that have presentations tomorrow, so I would not miss those. They're talking about similar subjects, also doing link prediction, another machine learning problem at scale. And Mats is talking about the fundamentals of the new features of GDS 2.S series, which will be machine learning pipelines and other cool things. And then I will leave you with some links here. And the slides will be shared somehow, so you'll be able to check this out in your own time. And I hope you'll find something interesting here. And I hope the presentation was useful.